Hi, everyone. Smaller crowd, unfortunately, than the last talk, but I'll take it. This is bigger than Kubernetes used to get at the ML conferences. So I think just as like a helpful level set and like starting place, I want to start by like kind of understanding how we got here over the last 10 years. Just so that I have like a rough sense of how to calibrate the topic, like how many people here like use Kubernetes in some way? Okay, so great, almost everybody who opted in. So if you like go back just 10 years, you get articles like this about like algos as a service. Like there was no such thing as an ML platform, and you kind of was like, okay, so like Google, how do you get identified in Gmail? Like Google has these like machine learning platforms which are just algos as a service, and you plug in some data and you get a model back and it like kind of works, and they're very single task and they're very focused on like run a linear regression. And this gets generalized a little bit, and like FB Learner Flow was Facebook's AI backbone, and again, this is also called an ML platform. And I think a consistent theme is going to be that at every single step, people call exactly what they have at that moment as like an ML platform. And FB Learner Flow was pipelines and notebooks mostly, which is like very familiar to the MLOps stack of today. At Facebook, you could request a notebook and do your work, and then you could build that into a pipeline, which is like an Airflow-like way to run your thing in production. And that gets productized by platforms like SageMaker, and this was announced in 2017. So they allow you to do hosted Jupyter notebooks that makes it easy to explore and visualize your data, and the 10 most common ML algorithms, and like that's all you need at that point, right? You have notebooks, and then if once you're happy with your like interactive data exploration, you shoved your data into 10 predefined templates, and then that was an ML platform. And so that's about 2017 to 2020. People realize like, okay, wait, this is weird. Like we forked this from like software engineering really way too far. So then you start, and this is our friend of the company who was the head of ML platform at Volvo, and he made this chart. And I made it slightly prettier, but you kind of have this like concept of like, I have a team mono repo that I'm going to develop against. You kind of like create a branch, and then you kind of test that, and then it gets to production, and you have continuous retraining, and you need this process where like you go through this regular developer process. However, we didn't solve all of it for Kubernetes, as I will get to in a moment, but the structure of this starts to look a lot more like software engineering. And then in 2022, in October, ChatGPT comes out, and no one does anything productive anymore in the ML space, and it's all about GenAI apps, and all of the people who pivoted make more money than I do, and so it's fine. And so where does that leave us, right? Like everything along the way has like produced an ML platform and has overloaded the term entirely. So you have Databricks and Snowflake who says like, we're your ML platform, they buy your CTO a steak dinner, the notebooks work great for interactive data exploration and the data is all managed, but like, I don't know if you can do production ML there, honestly, no shade. You have SageMaker, Vertex AI, Azure ML, which are some combination of like notebooks plus DAGs. You have Kubeflow kind of turned into Vertex, so you have Vertex pipelines and you have Vertex notebooks, and you have SageMaker notebooks and SageMaker pipelines and SageMaker training. It's like all mostly the same. You can make your orchestrator your foundational ML platform and try and do everything through orchestrators, and you iterate through resubmitting your orchestrator, and some of these orchestrators, especially the modern ones, let you do some amount of remote local development by step. You can SSH into a dev box, which is much like a notebook, but you can version control the code at least. There was Run AI, which was bought by NVIDIA, which launched notebooks. Metaflow is really great, and I like it a lot, and it's probably the best system other than Kubetorch, which we build. Ray was really popular. The Michelangelo talk was earlier. Uber, Pinterest, everyone built on top of Ray for a while. Some people have started moving away. If you want to adopt Ray, you have to move everything onto Ray, which can be pretty disruptive. And then Slurm is still around at academic institutions. But almost every single thing here is about how do you run Python on the cloud. And the cloud is increasingly based on Kubernetes, which are the blue stars. So you have notebooks, which are great for analytics and exploratory data analysis, but they lack scale, cannot be properly version controlled, and have poor reproducibility. You have DAGs and other you have DAGs and jobs. You have DAGs that allow for robust execution, reproducibility, but you translate into these DAGs from your research. There's long iteration loops. And it forces your programs into particular pipeline structures that can be undesirable. And then you have jobs, which are kind of like DAGs, but you just kind of put them all into one thing. And it's proper version-controlled code that can execute at scale. But you have really long developer loops that I can talk about in a minute, and you guys have probably already experienced. And so you kind of have two choices for your platform. You can separate the bottom two from the top one and have a really long research to production process, or you force everyone into the second one at gunpoint and your developers kind of hate you for the DevX of iterating through deployment. But before I get too deep there, I kind of start with two ground level, why Kubernetes? So most people here are already on Kubernetes. Maybe you guys already know why, but there's a couple of good reasons. The first is reproducibility. This one is fast. You want to package your stuff so that it runs over and over again and it runs in the same way. And tomorrow someone can check out your code and change it and push it back through and it will run again. If you cannot version control your code, it's really hard to have production. Second, scalability is really important. Kubernetes lets you launch and scale replicas, which means that which is important for training and for inference and for batch data processing and evaluation, et cetera. Even if you're not doing a multi-GPU distributed training, it doesn't really make sense to do hyperparameter optimization sequentially on a single node. You actually want to be able to run your XGBoost hyperparameter training such that you're parallelizing in 5 and then do it in 1/5 of the time rather than every morning having to sequence through it. We work with a Rexus team that kind of makes on-the-fly decisions about whether or not they want to use particular algorithms or hyperparameters based on the latest data. And so the ability to kind of do that quickly in parallel, even in a production setting, was pretty important. You want auto-scaling inference. Scale to 0 doesn't exist for SageMaker training because they charge you money when it's not scaled to 0. So they have very little incentive to provide it, but it's extremely table stakes in Kubernetes. This kind of horizontal auto-scaling of purely independent, embarrassingly parallel tasks also works really well for data processing. If I want to use Spark charges me a 50 to 100% markup, but I should be able to just define my processing service and launch it as replicas on Kubernetes, and then scale that to 0 when there's nothing happening. And then you kind of get scheduling and fair sharing of resources. Kubernetes comes packaged with a great scheduler. There's increasingly open source ecosystem tools like Q with a K, and then you kind of get this ability to kind of have your entire team collaborate. You can pool resources across interactive development and long-running jobs. It all works really great to help you scale past a couple of people that you can manage manually. There's no markups on GKE and EKS basically. They like that you're using their compute, so it's basically free. Yeah, Databricks marks up your instances by a lot of money. SageMaker marks it up by a little bit of money. Great businesses if you can manage it. We can't, so we're not doing it. But there's no markups, and so you save on the order of 20 to 50% just right off the bat by moving your services and workloads to Kubernetes. And then second, you bin pack those workloads, which is increasingly important in a GPU world. Azure, if you want to buy one A10, which has 24 gigabytes of VRAM, it comes with 440 gigabytes of RAM. That is enough to run a bunch of data processing workloads at the same time. But if you're forced into a VM-centric model, like on SageMaker, you do a job, it's one VM. Then all of this stuff sits idle. And the ability to bin pack into idle resources just also saves you on the order of 20 to 40%. Finally, the portability is great. There's increasingly many clouds. You have EKS, you have GKE, you have Oracle Cloud, you have Nebius, you have CoreWeave, you have anybody who wants to sell you compute, and mostly they will deliver to you in a Kubernetes cluster. So if your workloads are entirely portable on Kubernetes, you can replicate your platform instantly, and if you're a vendor locked to SageMaker, you will just take whatever they give you. Sorry, there's one more that I added, I forgot. And then ecosystem integration, the cloud native ecosystem is great. People think about Kubernetes in a very 2018 way where it's really scary to manage and poorly understood. Everybody in the platform world spent the last 10 years figuring out Kubernetes. Someone in your organization is probably really good at it. The observability is great, the logging is great, the management is great. The ecosystem is pretty much as rich as could be. But there is a catch, and this goes back to like why it's so painful to force people at gunpoint into job submission and pipeline-based approaches. That is that there is no local development. Kubernetes, if you think about web development, right, was built for the ability to kind of test your code locally. If I'm building a website and I want to deploy it with Kubernetes because I want it to scale and like serve millions of users, I'm still able to check how the alignment looks locally, feel good about how my website looks, test that locally, containerize it one time, push it through CI, it gets the staging, and everything is happy. Staging should look exactly like my local environment. We don't have GPUs attached to our machines unless you work at like Citadel. And then we don't have distributed compute. I don't have 7 computers on my local machine. I don't have enough RAM for the large data sets. I don't have local development. And so I must deploy my workload in order to develop with it. And that deployment becomes extremely slow in a Kubernetes setting because I basically have to push my workload through CI, republish my image, repull my image. And if you had pods running some service already and hit a bug, and you add a print statement, you're paying essentially a 30-minute loop to see what the print statement prints out. The other two are a little bit less important, but I'll just call them out. Availability and efficiency matters. ML development cares a lot about like where you're actually putting it, and the ability to kind of put it in a lot of places can be hard if you have built a rigid platform based on the assumption that some set of resources or installation is there. And then finally, and you're not using Kubernetes primitives, but you need to reproduce all of this like stack. That can be painful. And then like a single project end-to-end requires both online and offline activities, and that can be relatively painful for one person to like accommodate at an individual level. So therefore, you kind of get this like research and production introduction as well. I talked through this entirely already, that it takes 20 to 40 minutes. You can optimize your Docker container build. You can optimize your publish. You can optimize your pull. You can optimize your data loading from a mounted storage drive. But I've never heard anyone who can like restart a Kubeflow job in less than 5 minutes, right? And so like that's not interactive development. It drives people to things like notebooks that offer interactive development. And also, people loathe YAML. It just feels wrong, right? You're like writing a text document to like define your resources, and Python is the choice for 95%. I don't know if that's true. Like whatever. Who uses Julia? I bet no one here does. So then the question becomes like, what is a great ML platform from the context? Like if everything is moving to Kubernetes and there's all these reasons why you should do it, and there's this like kind of bad iteration loop, like what can we look at as an example of something that is good? And so I think Snowflake is actually a really great example of like powerful distributed programming made extremely simple. Before Snowflake, you kind of had a choice between like locating your job on a particular cluster, and if you ran out of disk space or you ran out of memory and like the jobs got too big, you waited for your ops team to kind of move you to something else, and then they would migrate your entire thing. And then for anything bigger than a single node query, you had a Hadoop team who managed just the Hadoop infrastructure, and like you probably had a guy or two just like writing Hadoop queries for you, and it was not fine. After Snowflake, because everyone was like, oh wow, we actually have a lot of data, you just write your SQL query, and it could be for 10 rows or it could be for 1 billion rows, and it's an identical SQL query. And then Snowflake kind of magically allocates the compute for you, executes it, and runs. And so I can log into like snowflake.com and run it in a cloud console. I can run it from a local Python process. I can run it from Airflow. I can run it from Argo. It does not matter. As long as I'm authenticated into Snowflake, I can take the identical code and run it at arbitrary scale exactly reproducibly. So there's no research or production gap there, and there's no iteration gap. It's because like there is some magical system that sits between me and the distributed computing that Snowflake runs to actually execute your query to make that process simple. So what does that kind of boil down to? You want to make heavy computation accessible and reproducible without opinionation. That means that you kind of want to give people an interface into Kubernetes that is much more accessible than the rigid interfaces that require you to kind of build a Docker image and submit a job. You want to make sure that it continues to reproduce across research and production, which have slightly different desires. But like in Snowflake, you can run your query really, really quickly in research, and you just take that and you put it in your orchestrator in Airflow, and it like runs fine. And then you kind of want to, like the propagating winds is a high level fluffy point. It's just like if you hire an intern, you should be able to like have them check out your mono repo, make a tiny code change, test that tiny code change, make a PR, and it gets to production. And they should be able to do that on their first week because software engineers can generally do that as well. So like obviously like the problem statements always lead up to like what do we do about it? And so like we're building a system called Kubetorch, and there's like a direct analogy between Kubetorch and Kubeflow. Like PyTorch and Kubetorch is the Kubeflow as PyTorch is the TensorFlow. Pythonic, modular APIs. It's eager, right? Like it's like instead of having a DAG like in TensorFlow 1, PyTorch was really nice to use because it's like eager and debuggable. It's general purpose and it has a rich ecosystem. Some of these things are also true about Kubeflow, so not exact an analogy. But you use Python, and I'll show you the code and the iteration loop in a moment, but you use Python to define the compute and like define what kind of distribution you want if you want distribution. For research iteration, we keep all the resources in place, and we have this extremely fast deployment process that takes less than 2 seconds to run locally developed code at scale in Kubernetes. And then in production, it all happens identically because you're taking your code and you're putting it onto remote compute. And so there's just regular Python programs that define your training, processing, inference, whatever, and some minimal APIs that just say, hey, take this and deploy it to Kubernetes for me. And if you take that, hey, take this and deploy it to Kubernetes for me and put it into your orchestrator, into GitHub Actions, et cetera, it does identically the same bringing up of compute and execution there. And so you can plug it into any system, right? So like, when I say Kubeflow, right, like Kubeflow comes with Kubeflow pipelines, so go ahead and use that. It comes with Feast for feature store, go ahead and use that. If you use MLflow, go ahead and use that. WanDB, does not matter. Like, it is strictly an interface to take your Python code and run it on the cloud in a way that is both interactive and reproducible. Some diagrams that kind of just reflect that. You check out your team repo, you edit some code locally, then you kind of call Python my class and it sends it there, and you call it a bunch more times and it sends it there really quickly, and that's what the 3 arrows means. I got feedback that it was confusing. And then in production, you put it to your Git repo. In your Git repo, it probably packages into a Docker image. That Docker image gets pulled down by an orchestrator or by CI or by a serverless function or whatever, and it calls it as well. But within the orchestrator or the serverless function, it doesn't really care about like what's happening in the program. All that serverless function needs to do is to trigger the execution on Kubernetes, and once that execution is triggered, the work is dispatched to the remote cloud again, and any production debugging that happens is just about checking out the code and running it from local, and what runs in your production orchestration is also identical to what runs locally. So like just briefly, like the distributed training APIs is like you define a compute object, then you take your train function or train class and send it to your GPUs. We also have a decorator class that people like more for inference. If you've like used modal before, you can think about it as a slow start, like modal on your own Kubernetes. You know, the decorator pattern is like pretty common, and you kind of just like run kt.deploy, and then you can just run it as is. So I actually have a little bit of a code demo here. So the magic is in scenes. So I have a distributed training here. I will make the font bigger so it's easier to see. So I have some train function. This is a fake training, but you should imagine this to be your training entry point. It could be your training entry point for basically any training. You can see that here in particular, I'm using a distributed process. I'm in a process group because I'm going to use Torch DDP, but you don't have to. You can be doing this with XGBoost or whatever. In here, I like trained for some number of epochs, and I made a mistake because I made a small problem. I misspelled a variable in my code, which is dumb, and this won't happen, but this just triggers a bug. So I've already brought this service up, and I'm iterating, and I introduced this bug. So if the internet here is good enough, yeah. So you can see that what it's doing is it's redeploying to my service, which is already warm. It's doing this hot deploy. If I had a good internet connection, it's 2 seconds, and a bad internet connection, it might be 5. But you can see here, I hit the bug. It propagates back to me, but this is happening on Kubernetes over 4 pods as a distributed PyTorch training. And so I say, oh crap, I misspelled this. I'm gonna undo my bad changes. I'm gonna make this change locally. I'm gonna rerun this code. And what you're gonna see is that within 5 seconds, all my changes are gonna propagate to my remote distributed training, and I'm gonna be able to see the training losses start printing back. And you will forgive that some of the training losses will be negative because it is a dummy example. So the propagation from local to remote is a little bit dependent on your internet speed. Oh wait, I turned off streaming logs. Whoops. But you can see that like the training completes and the losses are here, and those are the losses on each of my ranks. So your iteration process at scale is basically instantaneous. Like there is no development hit that I'm getting. And then when I move to production, like your production could be checking this into GitHub Actions and setting up a GitHub Actions that just runs Python, PyTorch, DDP in GitHub Actions, and that will just do the production retraining for you on a regular basis if you're just like picking up new batches of data and doing retraining. Or you could take this code, specifically you Dockerize this as a team monorepo, and you can just take this code and you put this in an orchestrator step in Airflow, and that will also just schedule this and execute as is. If you hit a production bug in Airflow, then reproducing it is just about running it locally, seeing the bug, making changes locally, and then getting it into your team repo, and then your bug is fixed. So that's kind of like the example here. And then like the last thing I'll say is like if you're working on complex issues, so I don't know, everyone is working on like a different slice of the ML world. I think we're also talking with people who are doing like reinforcement learning. And so like if you think about what reinforcement learning is, it's just really the hard mode of the ML platform in one like training loop. Because you kind of have your inference step, right? Like RL is like, you take some base model, you generate some like inference with it. You take those inferences and you put it into some evaluation service to generate rewards. You take those rewards and you put it into a training service and you do a training. You update your model and you take that model and you sync it to your inference service, and then it goes and it just kind of runs in this loop. So like if you're running like a code agent, right, you like generate some code, you have some like code tasks, you generate the code for it, you run it in your evaluation and sees if it runs and how many unit tests it passes. That turns into your rewards, you feed that into your training, and then your training updates the model and then feeds it into like, right? So like if you're doing something complicated like that, like how are you going to do that from a DAG setting? Or how are you going to do that from a Kubeflow PyTorch job setting? There's no way to orchestrate across multiple different services from a single controller in like a Pythonic programmatic way. And so like you don't need to be doing RL, but it's a little bit of like the representative case which brings together everything and answers the question like, hey, like why is it not good enough to just submit jobs, right? For many other reasons as well, jobs are not fault tolerant and et cetera. And I will just use the last minute to be like, there's fault tolerance properties here that I haven't shown. So for instance, you can resize your world size during a long running training. And because you're calling it from a driver program, you can just simply like take that and like accept it as a error, right? So you can do like, for instance, you can do trainer.train. This is a BERT training, but you can call your trainer class and call train. And if you hit like a worker membership change because the world size increased, or like the pod replica size increased, or if you hit a pod terminant error because you needed to preempt some of the pods because you needed to free up resources for some other process, you can just catch it as an exception. And in your code, you just recall .distribute, which restarts the process group with a different world size. And then you just continue training, and like, so then you like do this, it will restart your process group, and then what will happen is you'll just call this train again, and it will just start again, right? And this process takes about 15 seconds to restart a long running training, which like, I don't know, like if you work at a big company where you kind of have resource contention and like scheduling issues, and that people like go to sleep and wake up and you want to be able to like speed up or slow down your jobs based on the demand, like this just means that your driver program has this powerful programmatic control over your executing programs such that programs failures on the execution don't cause a teardown of all the resources. It returns control to your controller, and the controller makes the decision about what to do in the face of a fault on the remote program. So like, if you're on like a notebooks and DAGs framework, right, like the fast iteration at scale on Kubernetes makes sense. If you guys already have a sophisticated platform, you're like, that's not a big deal. But I do run at a scale where like fault tolerance is important. I think it is important to say that like the system will like scale from small scale 1 to 3 people, just like trying to get into a mono repo and doing code best practices, all the way up to like extremely at scale 1,000 node distributed trainings, which we've tried before, and like do it fault tolerantly in a way that allows you to do proper cluster management without layering. And if you're interested in like particular comparisons against like specific systems, we're moderately well educated about it. But yeah, so out of time and probably have no time for questions. But I'll be around.
Thank you, Paul. And I think we've got time until the next one, so about 15 minutes? Yeah. Oh, did you have a question?
Yeah.
For Paul?
Yeah, I'll take questions.
Hello? So how much does this cost, this Kubetorch? Or is it open source, or what?
It's a great question. We'll be in open beta as of tomorrow, and we'll be open source hopefully extremely shortly after that. I'll say that like we have a contract with a person who's very large and important, and they're like, we will not use you if you're not open source by the end of the year, and so we'll be open source by the end of the year. It's just a little bit tricky because as a startup, like making the decision about like building features versus like figuring out which features to cleave off and like keep closed versus open is like the wrong order of operations. So like we've been in like a private beta with like a number of people, but like in terms of like significant like enterprise or like at scale players, like a reasonable double handful of like people, right? Like double handful of people. And then like whatever, people are like poking around and playing around. Once we go to the open beta, like what we basically want to do is like tell people like, hey, like we are going to open source this, like you should be comfortable testing it, but like we are a company and we need to make money to survive, and so at some point like we need to figure out what features to charge for, because you don't want to adopt software and have it die on you because they make no money and they couldn't raise the next fundraising round. And so this is a long-winded, honest answer of like, hey, like open source is a little bit harder to like define, but like the team's background comes from open source. Like we've developed open source libraries before, and we have a contractual obligation to be open source, so it'll get there very quickly.
So how do we sign up for the open beta then?
You can just LinkedIn message me.
Oh, okay.
Yeah.
Awesome.
Like it's deployed by a Helm chart in a Python client. So if you have an existing Kubernetes cluster, you literally run like Helm install Kubetorch after you pull the Helm chart, and then you call like pip install the Python client. And both of them are just regular Helm charts and Python clients, and so no cost to set up. Like, I want to be careful because I'm like, hey, like we probably will have to figure out a way to charge for some of it. So like, for open source to like succeed, and now like it's a little bit of a soapbox. Like, I think it's like become a lot of an anti-pattern for like the open source development to be entirely sponsored by like Google and Meta, and like open source from like the grassroots has become like very challenging to do. And so like you see this like trend of like people like getting their seed round, going open source, getting 2 banner clients, and then like immediately getting bought by somebody. And like I feel like that's like kind of the anti-pattern. And so if you have good ideas about what should be open sourced, that would be like a really great outcome of the open beta, right? Like I think we are soliciting opinions in a way that it's like, oh, like if a company derives value, you should pay something, but like the open sourceness means that you're never locked in or at risk that like one day you build your entire platform on something and then you go like, actually it's 10 times the price, right? Like that's, I think, at the infrastructure level, that's like the existential crisis to not be open source, right? Like we know that like it's extremely hard to adopt a platform that you can't be confident in an extremely long period of time, but like how do you balance that against survival? So open to taking suggestions because it's not such a trivial question. This is like a meta conversation. Hopefully this was a helpful answer and not too like...
Oh, great, yeah.
Yeah. Okay, I can talk.